for the past 15 and odd years, and for the past 5 years I was into Hadoop and big data related technologies. And for the past 2 years, I have been, into Spark, and for the past 1 year, I'm extensively into Spark. Okay, so that's how my background. So basically, coming to domains, I was more into energy, clinical, okay, and medical, and recently we are starting with insurance as well. So that is coming to my domain expertise, and let's start. Okay, let me save this. Okay, fine. Awesome. So you guys can see the PPT. Okay, let's start. And so, this demo, we see why Spark, and we see the introduction and basics. And if time is within the limits, we can see some examples as well. So let's start with the introduction. So people are hearing about these two words predominantly for the past 6 to 1 year, like Spark and Scala. So what is this all about, Spark and Scala? So these two are there even before that. Then why people all of a sudden they're talking about Spark? Even when you say Scala. So Scala is a programming language. It is there even before Hadoop. Then why all of a sudden Scala is into limelight? Is because of Spark? Let us see. Let's try to understand. Is because of Spark, Scala is into limelight, or because of Scala, Spark is into limelight, or whatever. Okay, so let's move on. And if anybody asks me why I have to go for Spark, what is the problem with existing Hadoop setup? Why we want to include one more component on top of the Hadoop stack? I have only one slide to answer. This is the slide. So what happened? People started appreciating MapReduce. People started going around Hadoop and they started appreciating MapReduce, and they believed that MapReduce is one of the best things that is happening because it is purely distributed architecture. Both data is stored in a distributed fashion and the processing is also distributed fashion. So when we have such a finest framework running in Hadoop, why all of a sudden MapReduce, people started comparing, it doesn't work, it is not performing well, we need more and more sophisticated thing like Spark. So what's wrong with MapReduce? See, MapReduce is equally power as before. As a technology, MapReduce never changed. But what is the difference is, previously, if you say your data is like this previously, and people started processing data with mainframe technologies or central based technologies or normal distributed OLAP warehousing based technology or whatever, then your processing is like this. So this is your processing. So there is a slight inclination here. The graph is like this. It's not matching. So then people want the processing equally competent with the speed at which the data is growing. Then where we have something called as the data is same, but people started increasing the competency of the processing in the form of MapReduce. Now it is like this. Then people started appreciating MapReduce and Hadoop. Now the graph has become like this. Awesome. So graph has become like this and people started appreciating the MapReduce. It is doing extremely well. But all of a sudden, what happened now? The scenario is again gone into the root. So what is that? The data is like this now. And when it comes to processing, again the processing is like this. Back to same problem. Now this is the stuff is happening. So what happened? The MapReduce is equally powerful as before, but on the other side, the data is continuously, exploding. So why the data is continuously exploding? So what made the data to grow like anything? So there is simple reason. Only one answer we can say. That is nothing but IoT. People started thinking of IoT. IoT, we know Internet of Things, but slowly IoT has been transformed now into Internet of Anythings. So there is no restriction. There is no restriction. Anything can be, used as a source for receiving some data. It can be a relational application which is running and clients are entering some data. It can be a sensor information. It can be social media. It can be call center data. Anything is becoming the source of the data, and people wants to process the data. Previously, people wants to store the data. They want to archive the data. Whenever they want, they have to process the data. But now people, they want to archive the data, at the same time they want to process the data as it is. So if you want to have your processing engine to load such a diversified and data with such a magnitude, your Hadoop, which is just based on MapReduce, does not solve the purpose. So what made MapReduce to unable to perform such a data in such high magnitude? So what is the weakness of MapReduce? So what's wrong with MapReduce? That's what we have to investigate first. After that, we can see, so what is the weakness of MapReduce has become the plus point of Spark. So how Spark has changed its model so that we can, use Spark as just a replacement of MapReduce. So let's move on to the next slides by seeing one or two success stories of existing corporates. So this is the success story of Toyota. So what is the issue of Toyota? They are generating 700 million records every day. They have IoT enabled, and these are the main sources of information. One is the social media, the other one is the survey data, and the other one is their call center data. So every day they are just hitting 700 million records. It is too huge. Say when they are having their existing architecture, which is based on MapReduce, it is just taking how many hours? 160 hours. See, 160 hours is not a small thing. It's almost more than a week. So if I started my job now, I have to wait until the next week to get my results. It's quite a huge time. So what they have done, they have just rewritten the whole thing in Spark, and now when they are submitting the same job, now it is just taking 4 hours. Awesome. So almost they have achieved 90% of the performance enhancement. 90% of the performance enhancement just by replacing the MapReduce based model with Spark based model. So this is the success story of Toyota. Going forward, we have this, the Uber. So Uber, when they have presented their problem and they have challenges, and they have presented this in the last June in San Francisco, where I was one of the delegate participant of the event. So what they have done, for their New York server, they are accumulating 1 million bytes. Just for the New York server, 1 million bytes. That means the data is around 1 million. So what's, one second guys, I think I lost it. Okay. So what's the problem here? When they want to process it, they are having a huge problem. So the problem being here is, when they have, once again, why this marker is not working? Let me check. Okay, now it's fine. Thank you, guys. Okay. So the main issue of this is they have an existing model, which they're calling it as circa 2014. And they have the data coming from various sources, like they are getting the data from Kafka logs, and they are getting the data from databases which are schemaless or NoSQL stores, and they're having the database coming from schema, that is RDBMS. And they're doing some ETL processing which is used based upon Celery and Python, and then they're using some bulk loaders, using some tools, and they're doing all the infra maintaining in Amazon S3, and finally they're achieving it. But you know what happened? It is a very legacy thing. It is a legacy, and it will consume lot of time to derive their insights. So what are the three business insights which are driving the performance and success of Uber? These are the three. One is the calculating the Uber surge pricing, and then avoiding the drivers to avoid accidents, and to position the cars so that the driver get the maximum rights or maximum profits. So these three are the main things. To calculate this, they need more sophisticated thing which can process the data as it is. That means almost real time. So they need the real-time processing, almost mere real-time processing. So they have just replaced this with existing model with Hadoop and Spark. The data sources are same, but now they are processing the whole data just using Hadoop and Spark. So that's how they are achieving that processing near real-time, and they are able to calculate all these three things just on the go. So this is about one of the success story of Uber. Okay, then moving forward. So like that, you know, people started recommending Spark in many ways. Now it is up to our turn. Now we have to realize what's wrong with the MapReduce. So before that, a quick introduction of Spark history. So Spark was, you know, just a baby in the year 2009. So in the year 2006 we have Hadoop. Just after 3 years of Hadoop, now in 2009 Spark has been parallelly developed by UC Berkeley researchers or scholars. So what is the main core of Spark? This is the main core of Spark. Spark is something which is in memory. In 2009, and at that time we have something people started thinking of, you know, we have SAP, and SAP is accumulating data so much. Now people want to process and write some queries or whatever. For that they have an in-memory engine, in-memory warehouse engine, that is SAP HANA. All the industries started talking about in-memory processing. Similarly, at that time Spark, the people have started researching on Spark, and now Spark, the main fundamental of this is, instead of processing on the disk, whatever processing it has to do only in memory. And it is a common phenomenon that if on disk processing is 10x, then obviously in memory processing will be 100x faster when compared to on disk processing. That's, we know that. So that's why Spark is based upon in memory processing. And also, as Spark is provided by Apache, which is open source, people don't restrict the APIs to one particular language. They have APIs for Java, they have APIs for Scala, and they have APIs for Python. And now they have APIs even for R programming language. So Spark is having APIs for all these 4 programming languages. Then why people are going only with Spark and Scala is much popular when compared to Spark and Python or Spark and Java? Only reason is one reason. The entire Spark was written in Scala. So Scala is the best combination for Spark. It is very much easy for the Scala developer to understand the libraries of Spark and to work with. So that's how people started feeling comfortable while working with Scala on the Spark platform. That's why people recommend, majority of the cases, go with Scala. If a particular resource is basically from Java, and if the product manager or, you know, the solution architect is also from Java and they have more resources in Java, then they can implement Spark project by giving Java as a programming language. So there is no restriction. Every product may use Scala or every product may use Java. people cannot judge it. It's all open source, depends upon the complexity. But when it comes to percentages, about 90% of the Spark implementations are done in Scala. Around 5% of the implementations may go with Java, 3% with Python, and 2% in R. Like that, the percentage of implementations we have. That's why, that is the kind of a ratio. So let's move on. Now, this is the existing thing with MapReduce. We have to understand this. So what's going on with the MapReduce and what is the major drawback of MapReduce? That's what we can identify from this particular slide. If you are having a big Hadoop setup, you have a Hadoop cluster, right? In the Hadoop cluster, you have something called as HDFS. People call it as HDFS. Then, if you have submitted an application, the source of the application is coming from a disk, say for example. And from the disk, you are running a MapReduce job. Based upon the complexity of the application, the number of mappers will be decided. That we know that. Based upon the size of the data, the number of mappers will be decided. So each mapper, we know it is almost equivalent to one block. So what is the default block size of Hadoop 2? It is 128 MB. We know that, right? So if we have a large file coming from the disk, if the size is around 350 MB or 360 MB, if you are running one MapReduce job, obviously it will trigger how many mappers? 3 mappers. Okay, so it will trigger 3 mappers. Once the mapper has executed, the intermediate data which is coming from the mapper before going to the reducer, again it will be saved into HDFS. Then whatever data that has been written by the mapper exactly, yes, the intermediate data, okay, it's all temporary, we can say. This data will be read again by the reducers and they will do their operations, and whatever data that has been written by the reducers, again that result is also produced into HDFS. So if you have only one MR job running for a normal query, you have only one MR job. But for a complex query, for a large scale query, you have more number of MapReduce jobs. So if one MR job, one MR we can consider it as one iteration. The reducer part we can consider one more iteration. And again similarly you have one more mapper set of running on the data, that is called iteration 3. So like that you can have n number of iterations based upon the nature of the application. The underlying point here is all the intermediate data that is coming from the mapper is saved into the disk. Again it is read by the reducers. Again it is written into the disk. So here the total I/O which is happening is just happening on top of the disk. This is what.
Sorry, one question, Deepak here.
Yeah, Deepak. Yeah, Deepak. Yeah.
Can I ask?
Sure, Deepak. Always. Yeah.
So, okay. So we are telling SBFS. So it's a Hadoop file system, right?
Exactly.
Is that a disk operation or it's a file? Does it store on? I mean, when you are saying tuples, like it's a row kind of structure, right? I mean, it's not. I believe it's not relational database. It's just a file system, right?
Yes. So tuple means we can say one line. Okay, one line of data in that particular file we call it as a tuple. Okay, so it can be a relational data, or it can be a flat file, or it can be a CSV or XML, whatever. Here the order implies tuple means just one line or one record in a file. So whatever mapper is producing, mapper will produce you a part file. a part file. That is called part file. This is a file basically. So file will contain what? Set of records.
Yeah.
Okay.
Yeah.
So that is the meaning of tuple. So here on disk means what? Here the entire thing is distributed, right? The
Yeah.
Hadoop is always distributed architecture. The underlying storage will be on always
SDFS.
HDFS, right?
Mm-hmm.
So here what do you mean by HDFS? HDFS is nothing but the space available on the data nodes,
Yeah.
right? So whatever
Mm.
space that is there on the data nodes, that is nothing but your HDFS. So the mapper output can be written into the disk. So here the disk is not related to one machine. The disk is related to
This
the
is
total
SDFS.
HDFS. So one part file can be placed in one data node. The other part file can be coming from this mapper. It can be placed in a second data node. So there is no guarantee. The total output will be distributed across the cluster. Okay.
Yeah.
So the
So I
underlying
mean,
point. Yeah, yeah.
mhm.
Please go ahead. Go ahead.
So, but I mean, the input from stable storage, the first one, where the input started, right? I mean, just for
Yes.
clarification, I mean, that is something where we have already loaded the data into SDFS, and from there the mapper and the reducer are going to
Uh,
work. Is that correct?
yes. 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 So this here, this
Mm-hmm.
input table storage can be your HDFS. Okay. It can
Yeah.
be HDFS because a MapReduce job can load the data from HDFS and it can finally store the data into HDFS. So your input can be HDFS. Apart from HDFS, it can be your relational database.
Oh, so
Okay.
Hadoop works
And it
directly on the relational
can be
database
some
also, right?
it can be some FTP. Okay. Anything it can be. Okay. So from relational database also, if you want to load the data, like we have something called what? Scoop. Right.
Yeah.
Yeah, Scoop. So what Scoop will do, it will load the data into HDFS. So when you
HDFS.
run a Scoop job, what it will run? It will run all mappers. Based upon the size of the table, it will trigger number of mappers.
Okay. Got it.
Okay.
So
So
basically
whatever
input to mapper is always a HDFS. So before
ex-
that through scoop or flumes or whatever, we just
ex-
first load the data into HDFS. After that all operations happens. Is that correct?
100%, absolutely
Okay.
right.
Okay. Thanks. I absolutely zero information on Hadoop. I have not done any course. So whatever I have just read from here and there. So probably I'll be asking some questions on
No
Hadoop.
problem. Please, you're always welcome to ask the questions. Okay.
Thank you.
And Balaji also. And I think Balaji has some knowledge on Hadoop. So I think he's good. He's replying me in the chat. Whatever he has replied, 100% is good.
Yeah.
And coming to the Spark. So in the Spark, we are not changing the pattern here. We are getting the data from HDFS for Spark application. But the thing is, instead of writing the data into HDFS or onto the disk, it is writing the data into what? Distributed memory. Okay. So what is the distributed memory? This is not a disk memory. This is the in-memory. The in-memory. So what is this distributed memory and how Spark will benefit from storing the data into this distributed memory? That's what we have to investigate. So just as a comparison between the previous iteration and this current iteration, you can just remember in MapReduce, all the data is coming into the tuples in the form of and onto the disk. But now in the Spark, instead of onto the disk, we are getting the data into distributed memory. And previously we know from this slide that distributed memory is almost 100x, sorry, the in-memory is almost 100x faster than, hello?
Yeah. Yeah.
Yeah, the in-memory
External
is
data.
always 100x faster than disk-based memory, right? That's we know that. So by
Yeah.
looking at this, we can say that Spark is faster than MapReduce. The only reason being is all the intermediate data instead of writing into the disk, it will write the data into
temporary storage in the memory.
the in-memory. It can be as temporary storage, of course, but that is not written onto the disk, but rather it is writing the data onto the distributed memory. Okay.
It's
Now,
RAM, right? RAM of a
exactly. So now lot of questions may arise. Like, just Balaji got one question. He is mentioning if there is a failure, how to overcome it. Okay, so let us compare. There are a lot more things. Even the question is right, but at this point we are too early to discuss about that. First of all, we have to understand how the Spark execution will be happening. Then we will get the 100% idea of how Spark will deal with failures and how Spark will deal with other facilities that are provided by your Hadoop MapReduce. So coming to the Spark execution model, we will call something as a driver program. This is the starting point. Like if you are writing a Scala program by using some Scala IDE or some notepad or whatever, so that is your driver program. Your Spark application written by the developer is nothing but the driver program. In the driver program, the program will create something called as Spark context. This is very important here. So what is this Spark context? Spark context means, say if I want to talk to a database, first of all I have to create what? Connection, yes or no? Obviously, without creating the connection, I cannot speak to any database. That is 100% true. Similarly, if I want to speak to Spark, this is my application and this is my Spark setup. So how can my application speak to Spark? That means just by creating a Spark context in my application. So once I have created a Spark context in my application, then my program is able to talk to cluster manager. Okay, so what is the cluster manager? This is again a question. In Hadoop, what is the cluster manager? We are using YARN. YARN. So YARN stands for yet another resource negotiator. YARN. So what the responsibility of the YARN? It's quite simple. In Hadoop there are a lot of animals. One famous guy told Hadoop is nothing but a zoo. That's why in Hadoop we have something called a zookeeper, because we have a lot of animals. We have honeybees, we have elephants, we have flies, we have pigs, right? So what I mean that? I mean that we have pig, we have hive, we have Uzi, right? So we have MapReduce, so many things are running. So who is going to provide resources for each one of them? YARN is going to provide. So YARN is a resource manager. If an application wants memory, it will allocate memory. If an application wants CPU, it will allocate CPU. If the application wants some HDFS space, it will allocate some HDFS space. So whatever resources an application wants, so basically it will allocate it. So that's why it is called the resource manager on Hadoop. So if you are installing your Spark on top of Hadoop, obviously your YARN will be your cluster manager for Spark as well. Okay, so any request which is coming for execution, it has through cluster manager. Straight away it cannot run on any other nodes. Okay, the request has to come only through the cluster manager. Okay, now once the request is through the cluster manager will verify which of the node is free at that particular point of time. The request will be processed on that particular node. Say in Hadoop, we call it as a data node. But when it comes to Spark cluster, we don't call something as data node or name node. We call it as a worker node. So what is this worker node? Worker node is the one which actually executes your application. For that purpose, worker node will have a daemon running called executor. So what this executor will do, whatever your program is coming, it will split the program into tasks, and each task will be executed by the executor. For this, all the intermediate data has to be written into the distributed cache, that is called this cache. So all the intermediate outputs, or if you want to persist whatever, we can use the cache of this particular executor. Please ask some questions on this slide.
Yeah. Hi, Deepak here.
Yeah,
Yes, couple of questions. Okay, so you told if Spark is working or Spark is installed on Hadoop.
yes.
I mean, what do you mean? Does Spark work with?
Installed on top of Hadoop means, okay, so for that, let me open one Hadoop slide for you, okay, because you are new to this thing. So where is the Hadoop slide? One slide, I will open. Okay, it can be anything, reading or writing, doesn't matter. Just want to, yeah, okay. So, see, this is the typical Hadoop cluster setup. But here it is. See, this is the typical setup of a Hadoop cluster. Okay, in Hadoop there are so many things. One is called name node, and all the data will be saved inside the data node and processed in the data node. Right. So
Yep.
where the data is stored in Hadoop, the question, and what is the answer? It is just on the data nodes. This is the data node, and where the data will be processed, again it is on the data node. So whatever is happening in the Hadoop, it is happening only on the data node. Okay, so why it is not taking this? Sometimes this annotation is not happening. But it's not happening. It's okay. Yes, now it is good. Yeah, so this is the data node. Okay, now if I want to add Spark into my existing Hadoop setup, okay, so if I want to include Spark into my existing setup, how to do it? I don't have, I don't buy special hardware just for configuring Spark. It is too costly. So whatever is my existing setup, on the same setup, I will configure my Spark. So what is my existing setup? My existing setup is nothing but my data nodes. So on my data nodes, I can configure my Spark. On my name node, I can configure my Spark master. So in Spark, we have two things. One is called Spark master. The other one is called worker nodes. Okay. So Spark master, where I can configure it on the name node. And worker nodes, where I can configure on top of data nodes. Okay. So here I can configure my worker nodes like this. And here I can configure my Spark master. Okay, so if Hadoop is using Yarn as the resource manager, when I am installing Spark on top of Hadoop cluster, obviously what is my resource manager?
Cluster manager.
Yes, that is nothing but Yarn. Okay, clear?
No, sorry. So it will not replace Yarn, right?
No, it will use the services of Yarn.
Okay, only. But cluster manager will be on top of Yarn, correct? I mean, it will give instructions to Yarn.
Your cluster manager in this case is nothing but Yarn.
Okay, so it will interpret. I mean, it will work in the same way. Okay.
Exactly. That's true. So going back to our Spark.
Here also any job tracker, task tracker, all these things will be there during processing.
We don't have job tracker or task tracker. If we want to monitor the job, okay, all we need to monitor the job only to the application master or master, Spark master. We have something called as Spark master.
Anyhow, I am very early to ask you this question. Sorry.
No, that's okay. Not in early, this is the right time this time. So we don't have any application master. In Hadoop, we have something called as application master, where you can track all the applications, right?
Yes.
In Spark, there are two things. Okay, if you are submitting your application to the yarn, you can track your application to the yarn application master. Okay, so there are two things. Okay, in Spark you have a flexibility because Spark is installed on Hadoop. That means you have two things. One, you can submit your application to your Spark master, or you can submit your application to your yarn.
Okay.
Okay, so if you are submitting your application to the yarn, just like any other Hadoop application, you can track your application in the application master homepage. Okay,
Okay.
if you are submitting your Spark application to the Spark master, you have separate user interface called Spark master UI. There you can track it. Okay,
Okay.
so that is the meaning. I will show you. Okay, so you can track either with application master, or you can track your application progress either using the Spark UI. Okay, both are possible.
Okay, one question, like this caching, whatever is happening in each of the worker node, right? So
Yeah.
we saw in the previous slide, like the processing happens in real time, sorry, I mean in memory, right?
Exactly.
So does that much of memory available in I mean I believe, I mean we are processing, we were talking over here in huge data, right?
Absolutely.
So I mean, do we have that much of memory? I mean, compared to the data which is stored in file system to process it.
Awesome question. So here there are two things. One is data storage. The other one is data processing. Okay. You don't process all the data which you are storing, right? The data will get that you have the data, incoming data, the data gets processed and you store the data. Once the storage happens, once the processing happens, the data will move from your processing layer to your storage layer. Yes or no?
Yeah.
What is your storage layer in Hadoop?
HDFS.
HDFS. Okay. What is your processing layer in Hadoop? You have many things. One is your MapReduce. Now we are Spark, right? Your pig or hive or whatever. So once the data flows into the storage layer, sorry, the processing layer, once the data got processed, again it has to dump it into
HDFS.
obviously. So even though you're implementing Spark, Spark will only process the data. Once the Spark processed the data, it won't hold any data. Finally, the data has to be dumped into HDFS or Hive. There are the targets of your Spark, HDFS or Hive, and we see even Cassandra. Okay, NoSQL database. If you want to store the data into Cassandra, we have to push it here. Or if you want to store in some relational database straight away, just push it into your relational database. So Spark don't hold all the data what it is going to process. Okay.
So we are saying, I mean, if I'm not wrong, if I understood it correctly, so the only difference is what, like Spark is, I mean, cleverly using the in-memory of the
Yes.
machines, whereas Hadoop was completely working on the directly on the disks only.
Yeah,
It has
not
never
Hadoop, MapReduce. Yeah.
yeah, MapReduce, yes. So it was
Yeah, yeah.
never using the the in memory of each node. That is the
Yes.
difference, right?
Exactly, 100%. You're right.
Okay.
So what is you mean by distributed cache? The distributed cache is nothing but once you are installing your worker nodes, okay, like this, if I have one worker node and there is another worker node, two worker nodes and three worker nodes.
Teacher, Nagar's
The
here.
RAM.
Okay, Nagar's here. I have a question back to Deepak. I'm sorry, but I'm okay. So back to the Deepak question. Where is the situation is that when there was a failover, when so what will be what it will be taken care when the failover in between when it is processing data from.
Yeah, failover is obviously it is a common phenomenon. Okay, now everyone is clear what is this distributed cache, guys?
You were explaining something.
Yeah,
Sorry,
I'm
you were
going to explain what you mean by distributed cache. After that, I will come to the failover. Okay. So distributed cache is nothing but the RAM of your worker nodes, the collective RAM available on all the worker nodes. Okay, that is called your distributed cache. The cache available in worker node 1 and the cache available in worker node 2 together, I will call it as a distributed cache. Okay. So what is the typical configuration of a Spark worker node? Or if I want to install a Spark worker node on a piece of system, what is the configuration that system should possess? So this is the typical configuration of a system. It can be acting as a worker node. So there should be 32 cores minimum, 32 cores, CPU cores, and it should have a 256 GB of RAM. Hard disk, it can be 10 TB or whatever based upon your size of the input, you can have it. Okay, so this is the typical configuration, 32 cores, 256 GB of RAM and 10 terabytes of hard disk. Like that, if I want to establish a 10 node Spark cluster, so what is the total in-memory capacity of my RAM? 256 into 10, almost it is coming to 2.5 terabyte. So that is the capacity of my in-memory and of my entire Spark cluster. So at any given point of time, I can hold 2.5 GB of data in my RAM. Okay. So that is the meaning of distributed cache. That's fine. Now, what happens? Something is failed. That's what we have to understand. So before that, see how many slides we are skipping. We have to see what is RDD. We have to see what you mean by caching. Then we have to see about fault recovery. So still we are little early for this question. Okay. So let me complete RDD. Then only we can understand what is happening with the fault recovery. Okay, guys. The failover or all those things. So in Spark, any piece of data, this is called my distributed cache. Okay, any piece of data, it can be a data coming from a relational database, it can be a data coming from a file, or it can be a data coming from some Kafka, whatever. Once the data has landed into my distributed cache, the data I will call it as RDD. So what is this RDD? RDD stands for resilient distributed data sets. So the data is distributed, the data is resilient. Before going to the resilient, we have to see how the data is distributed. See guys, this is crucial. Please try to understand. If you have any questions, just pause me. Now we are trying to see how the RDD is distributed. So this is the basic hierarchy of an RDD. So what is an RDD? An RDD is nothing but collection of partitions. Partition 1, partition 2 and partition 3. Something like that. An RDD can have n number of partitions. So what is the partition? The partition is nothing but piece of data. You can consider this as an array. Okay, and we have some partition like this, and this is one more array, and we have one more partition like this, and this is another array. So these are called my partitions, partition 1, and this is my partition 2, and this is my partition 3. Then what is your RDD? An RDD is something like this, which contains the reference of my partitions, and reference of my partitions, and reference of my partitions. This is my RDD. So when you load a data, you have a very big data. Say you have a data of size 350 MB. 350 MB of CSV file you are loading into your Spark. If you are loading a 350 MB of CSV file, it is too huge. So it will be split up into 3 partitions. So the total 350 MB of file, once you load it into Spark in memory, it will be created into 3 partitions. And now you are naming this as RDD. So if you have 2 worker nodes in your Spark cluster, for example, then your partition 1 can belongs to worker node 1. Partition 2 can be saved in worker node 2. And again partition 3 can be saved in worker node 1. Like how your data will be saved into different nodes. Here data nodes in our Hadoop. Similarly, one second, I want to switch back to Hadoop. Oops. So this is your Hadoop, right? So in Hadoop, if you are writing something into the Hadoop environment, whatever you are going to write in the Hadoop environment, the data will be get stored here, right? So one piece of data will be saved in one data node, and if the data size is too huge, the same other data can be saved in some other data nodes. So what is this? This is called replication. Replication, and one more thing is the data is fragmented. The data is just distributed. So instead of storing the whole data on a single data node, I am splitting the data into blocks, and one block I am saving in one data node, and the other 2 blocks I am saving on 2 different data nodes. Similarly, in Spark, if you are processing some large data, as I have mentioned, the RDD is nothing but set of partitions. So each partition can be saved in a different worker node. Like for example, here we have 2 worker nodes. So if I want to save the data coming from the CSV file, and one partition I can save in this worker node, and the other partition I can save in this worker node. So what is my RDD? My RDD is nothing but references of my partition which is saved in worker node 1, and the reference of my partition which is saved in worker node 2. So that's why my RDD is called to be distributed. Any questions on this RDD?
I have to.
Yes.
Can I? Okay. So who manages RDD? Is it cluster manager?
Which one?
RDD. Who manages?
RDD will be managed by your master, your Spark core itself. Okay, only your applications will be monitored by your master, and your cluster manager is only responsible for the resources. But your RDD will be monitored by whatever is the executor that is allocated for it. It is able to, one second, wait, it is not going. Yeah. So this is responsible for the RDD. Okay, so your executor is responsible for the RDD. Okay, so each RDD will be created and it will be available for the executor. Okay. So many applications can create many RDDs. Okay. So whether the RDD is fine or not, whether the RDD is how much amount of storage it is having, and the RDD metadata, that is called a lineage. Okay. So everything will be maintained by the application, by the application instance, not by your cluster manager.
How the metadata also, how the metadata will be, RDD will maintain the metadata, or it will not maintain?
RDD is only the data, but metadata about the RDD is called the lineage. Okay, so that lineage will be maintained automatically. Okay, so not only for one RDD, whatever RDDs that are running on the cluster, for all the RDDs, the lineage will be maintained in the form of a DAG. Okay, that we see it. Okay, that is called as a DAG. So what is a DAG here? DAG stands for direct acyclic graph. Okay, that is the metadata. The metadata of any RDD will be maintained in the form of a DAG.
Okay.
That's a separate machine.
No, that is not a separate machine. The information is maintained on the Spark cluster itself. Okay?
Okay.
But it will be maintained on the disk. Because if it is maintained on in-memory, if something went wrong, you will lose the metadata. Right?
Yeah.
So it will be maintained in the local files. It will be maintained on
Hadoop, the master node will be maintain the metadata generally.
Exactly. Master node will maintain the copy. Yes, exactly. But see here, what is the master here? Spark master. Okay?
Okay, okay, I got it.
Yes. So,
Sorry, I think
yeah,
last
please
question.
ask.
Yeah.
No problem.
So,
Give me any number of questions. Okay. Yeah, please ask.
So RDD will be having reference to the partitions, right? And those partitions might be on different nodes, correct? So suppose like so it might happen like I have been given 10 jobs at a time, or 10 jobs been executing. Okay, so probably those 10 will be having 10 RDDs, right? If I'm correct in my fundamental understanding. So
what is that? What is that RDD?
no, so there will be 10 RDD, which will be, suppose I have 10 jobs to submit. I submitted 10 jobs, 10 different things. Okay. So there will be 10 RDDs created who will be having, different tasks being assigned to different partitions, right? They will be having separate partitions, correct?
Of course, yes.
Yeah. So those 10 RDDs, are those RDDs all been maintained in that master node, or sorry, in that what do you say, DAG or something you told, right?
See, the RDD metadata will be maintained by the master. But where the RDD will be saved? The RDD will be saved in the form of partitions, and the partitions are spread across all the worker nodes in the cluster.
Yes, got it. Clear. That's what I'm telling. But the information about those pointers will be stored in that DAG, right?
Exactly.
The partition, I'm telling the reference to each partition. Okay, so this is job 1 or job 2 partition. Yeah.
The reference to the partitions will be saved in the RDD, and the state of the RDD and the metadata of the RDD, like how many partitions the RDD is having, how the RDD is generated, what operations are performed on the parent RDD to get the child RDD, the every metadata, that is called lineage. Okay. I'll come to that. Okay, so once an RDD is generated, if we want to save it, persist it, so where we have to save the RDD? By default, the Spark is in memory, so all the RDDs will be processed in memory. That is option number 1. And if you have configured memory and disk, what happens? As long as you have so much of memory available, it will store the RDDs into the memory. But if you are running out of memory, then what it will do? It will dump the existing RDDs into the disk, and it will use the available memory for the calculation. Okay? That is called memory and disk. It will use both. And if you want to use disk only, it doesn't use any in-memory engine. It will only store the intermediate data, and all the RTDs will be saved only into the disk or to the machine on which the worker nodes are running. And similarly, if you have configured the persistence as memory only 2 or memory and disk 2, then for every piece of RDD, it will create one more extra copy. Like in Hadoop, you have replication. For every piece of block, it will create 2 more pieces of blocks. Similarly, in RDD also, for every one RDD, it will create one extra copy of the RDD. So that is the fourth use case. But majority of the case, we only use option 1 and option 2. Okay? We don't use 3 and 4 because 3 disk. If you are using disk, then what is the purpose of going for Spark? And memory is too costly. Maintaining one RDD is very much costly. Based on that, if I want to maintain one extra copy of the RDD, unnecessary headache or overhead on the memory. So people don't prefer option 3 and 4. People only prefer option 1 and 2. Okay? Now coming to the fault recovery. So coming to this fault recovery, there are basically two things. Okay, what Hadoop follows and what Spark follows. So in Hadoop, what Hadoop will follow? Hadoop will follow the concept of fine-grained, recovery. What do you mean by fine-grained recovery? Say for instance, I'm unable to draw it here. Are you able to see the annotations?
No.
All of a sudden everything is coming up. Okay. So here Hadoop will follow the recovery standard as fine-grained. So what do you mean by fine-grained? For every block you create 2 extra copies. If something went wrong with the original data, still you have 2 more backup for the data, right? That is called fine-grained updates or fine-grained strategy. But in Spark, we don't use fine-grained. We use coarse-grained. So what happens in coarse-grained? If you have an RDD, and what happens if RDD is lost? I don't have any other RDD. So what I have to do? Instead of storing the RDD, I will store the lineage of the RDD. So what do you mean by lineage? Lineage, or we can call it as some metadata or whatever of the RDD. So what is the lineage here? The lineage is something, here we can mention. Okay, so the lineage is nothing but the process from which the RDD is generated. That is called the lineage. So instead of maintaining the data, if I maintain the process, if the RDD is lost, if I apply the same process so that the RDD will be recomputed. Okay, I have variable called C, I have variable called A, I have variable called B, and I say C equals to A plus B. That is my result. Option number 1, for every C you store 1 more extra copy, or option number 2, which Spark follows, don't save extra copy of the result, just save the process. So what is the process? I only save this formula. So whenever I lost C, I will just again apply A plus B. I will get the C. Got it?
So I'll have to go back to HDFS to get the data again also, right?
Yes, we run the same. It is the automatic process, okay? It will be run the lineage. Like the lineage here, say there are 2 of RDD, okay? So what are the operations here? One is the transformation, the other one is the action. So transformation is what? Transformation is something, mapping. That means what? If you have a RDD, 1, if we apply a transformation on RDD1, you will get 1 more RDD that is called RDD2. So for this transformation, this RDD1 is the parent and RDD2 is the child. And on RDD2 we have applied one more transformation, then you will get RDD3. For this transformation, RDD2 is the parent and RDD3 will be the child. Okay, then what is our lineage? This lineage is nothing but this information. If for RDD3, what is the lineage? This line. For RDD2, what is the lineage? This line. Okay, that means what? Whenever RDD3 is lost, we maintain the lineage. In the lineage, what is the information that is maintained? On RDD2, you have applied a transformation called T2. When you apply a transformation T2 on RDD2, you will get RDD3. That is the lineage of RDD3. Understood? So if my RDD3 is lost, automatically T2 will be applied on RDD2 and again it will generate RDD3. Clear, guys?
Yeah.
That is called lineage information. So this information we are going to see in the DAG graph. Okay, it will maintain what are the transformations and each and everything. We are going to see in detail in our sessions. Okay.
Okay, thanks.
Now, I think someone is asking a question. I just want to complete these transformations. What is the question? What is that question, guys? Someone is referring to? So any questions so far?
No, nothing from sir.
Now coming to, yeah. See, coming to the system requirements here, guys. See, if you see here, I have allocated, this is the virtual machine. If you have a Cloudera or if you have Hortonworks, we can use it, or else if you have Ubuntu, and we can start installing everything on Ubuntu. So this is the recommendations for the VM. You should have, I have given around 7.5 GB of memory and 2 crores and 38 GB for the hard disk. Okay, just for the VM. So hope you have enough hardware in your laptops. Yes or no?
What would be the minimum this one?
The minimum memory of your laptop should be, in the worst case, it should be 8 GB.
Oh, that is the worst case.
Yes,
Okay.
absolutely. In the worst case, if you have 8 GB of RAM into your laptop, at least you can give 5 GB of RAM for the virtual machine.
Okay, okay. And is there any other way, like you told Cloudera or something, right?
That is also VMs. In Cloudera, minimum, your laptop should have minimum of 12 GB. Because Cloudera VM mandatory recommendation is 8 GB. If you give less than 8 GB, the VM won't start now. The recent versions of Cloudera.
Okay.
For Hortonworks, you have to give minimum of 4 GB of RAM for Hortonworks Sandbox. So as a overall, your laptop should have 8 GB.
Minimum, right?
Yes.
Okay.
For Hadoop, if you have 6 GB of RAM, that is fine. But for Spark, you need more memory.
Actually, in my system Ubuntu I have only 4 GB RAM. Still means I'm able to log in VM Ubuntu actually.
Yeah, that is fine. You have a machine and you have installed only Ubuntu on top of it. You have only 4 GB of RAM. That is fine. But once we start installing Spark and Kafka and other services, Spark Master, okay, and we install some tools called Zeppelin, we install so many things, Cassandra, okay, we install Active-MQ, we install JMeter, so many things we are going to install in these sessions.
Yeah.
And we have to make them all running in our use cases.
So you have to buy another laptop itself.
Why we have to buy? Just increase our RAM.
Is this going to support or not? I'm not sure. Need to check it. Okay.
One more 4 GB it will support, I think. Whatever old is your laptop, it may not support 16 GB, but it will have one more extra slot. You can have one more 4 GB into it.
I have 4 GB actually. This one.
Into
So
2 slots?
that I don't know. I need to check that.
You can go and verify. But if you are seriously, if you want to do something on big data, you need big RAM. Yeah, or else if you have any Amazon Access, AWS, there if you have, that is also too costly, right? People, it's too much costly if you want to have a cloud hosting of your VM.
Hardly 2000 Deepak, 4 GB if you add it, there will be 2 slots definitely.
Hmm?
Yeah, I'll have to check.
Yeah, that's too, Balaji. Yeah, you're right. Open Cloud Era. I have all, you have to download it. These are the things which cannot be shared. They have to be downloaded from the internet. I will share you the links also. Okay, see here. Memory is 8 GB. That's the 8 GB does not take further. Okay. Hard disk is 64 GB, and of course we can give 1 or 2, that doesn't matter. Okay. So that is the minimum recommendations that are needed. Okay. And also I will cover all the, before going into Spark we have to see the Scala language. Okay, Scala you don't need that much amount of RAM or memory. Okay, it is very lightweight. Even in Windows also we can install Scala and we can start practicing Scala. That is not a big deal. But for going forward, when it comes to Spark, by that time you have to upgrade your system.
Okay.
Okay, so what is our plan of the course? First, initially we start with Scala. Once we are good with the Scala, then I will start Spark core. On the Spark core, we see the main stuff, how to create a Spark application, how to submit to Spark master, how to track the Spark application, how to see the DAG, and how to see the tasks, everything. You will get 100% idea what's happening in the Spark world once we're done with Spark core. After that, we see the Spark SQL. There we see getting the data from different sources and storing the data into Hive or storing the data into Cassandra. All this connectivity and all these things we will going to deal with. And Spark streaming. In Spark streaming, we deal with how to get the data from Flume and how to get the data from Kafka, how to get data from Active-MQ, JMS, okay, and how to configure Flume and Kafka, and how to store the data into HDFS and Hive. That all we see, okay. And also, as an additional thing, I will explain how to connect this data to Tableau. Okay, because Tableau report developers will be there. But as a Spark and Hadoop developer, that is your responsibility to make the data available for them. So for that you have to connect your, Spark or Hive components to the Tableau so that they are available for them. So that thing we will discuss. And Zeppelin, this is very much, latest thing happening in Spark world, and Hortonworks is supporting a lot this Zeppelin. So Zeppelin is an analytics and graphical tool. That also I will show you how to install and configure. And Cassandra, how to install and configure and how to get the data from Spark into Cassandra. We are going to see it. And after that, what else you need? Of course, I will provide you FAQs on interviews and your resume preparation. Everything, almost all we are going to cover. Okay.
Okay.
Can I ask one question? Hive is running under MR only, no? In the Hadoop environment, Hive will be part of background is MR only, no?
Exactly. Hive, your pig. Okay. Whether you run Scoop, whether you run Hive, whether you run Pig, whatever you run, it is nothing but your map reduce. Okay.
It is also means the Spark also it more or less will be in a JVM only, Java Virtual Machine. Under that only we execute that Spark and all this.
Anything is JVM because we need the container, right?
Yeah.
Container. That container is nothing but your JVM. But where the container will be launched? Executor. Okay? That is our executor. We don't call it as a container, but here we will call it as a executor. So it is all, you know, we have an application. This application based upon this, it will be allocated an executor. What the executor will do, it will split the application into tasks. Okay? Tasks. Each task will be executed by the executor. So who is going to execute? You need environment. So that is nothing but a CPU cores. Okay. So if you have a 2 cores, see here, this is the machine. How many cores I have assigned?
2
cores. Okay. So I have 2 cores. If I have 3 tasks, one core will be processed by, one task will be processed by one core. So at a time, how many tasks I can process in parallel? Guys?
2. Sorry, can you repeat?
At a time, if I have 2 cores and if I have 3 tasks to be processed by the executor, at a time, how many tasks I can process in parallel?
6.
2
No.
2 processors.
The answer is very
1.5.
simple. One core, one task, always. That is one-to-one mapping. Okay? If I have 4 tasks, if I have 2 cores, at a time, how many tasks I can complete?
2.
2. Only the remaining 2 tasks will be in waiting state. If I want to achieve more parallelism, how many cores I have to allocate?
4.
2 more we need.
4. So that's why if a machine is having 32 cores, how many tasks I can run in parallel for the executor?
32
tasks. Understood?
Yeah.
That's why the more number of cores, the more number of parallelism you can achieve, the better will be your application. Okay?
Yeah.
That is the relation between your CPU cores and the tasks. We are going to see it, okay? That's not everything we are going to see in practical.
Yeah, that is what important.
So